Hello everyone. Today the lesson is going to be about something called theoretical probability. But before we get to that, let's just start with what we know so far. The last few lessons we've been talking about experimental probability, and experimental probability is the number of successes divided by the number of trials. Now the thing about experimental probability is that depending on who's doing the experiment, if for instance somebody rolls a die 10 times and then somebody else rolls a die 10 times, they're not necessarily going to get the exact same results. They're the correct results for their experiment, but they won't be the same. Now, the thing is, there's another type of probability which is called theoretical probability. And with theoretical probability, what we measure is very, very similar to experimental probability, but you'll notice that the denominators are different. Here it's the number of trials. Here it's the total possible outcomes. And what this does is it makes this kind of probability, so I'm just mentioning here to notice that small difference. It's what should happen. Okay? Theoretical probability is what should happen. So if everybody was rolling the die a billion times, what would be the probability of getting a 1? Or what would be the probability of getting a 2? And that's what theoretical probability measures. And theoretical probability should be the same for everybody. So my example here is on a 6-sided die. What is the theoretical probability of rolling a 1 or a 5 or any other side? Well, what are the possible outcomes? So in order to help us visualize what the possible outcomes are, and I'm sure some of you may already know, is we use a probability tree to do that. Now, probability trees can be a bit of a difficult thing to draw because of space issues. So I'm going to show you what I mean by that, especially with one of the follow-up examples that's coming up. This one's not so bad. So you have a die. What are the possible outcomes of rolling a die? And what I mean by tree is we draw these branches off of that, whatever we choose to use to represent this die. So there are 6 possible possibilities when you roll a die, because there are 6 sides on a regular die. If you think of a deck of cards, there are 52 cards in a deck. The tree would be a little bit hard to draw if you had to draw 52 branches here. Okay. So what each branch of the tree represents is each of the possible outcomes. So as I said, there are 6 possible outcomes for rolling a die. So one branch would represent the event we'd be interested in. So the question could be asked, I think I do ask it here, for a 1 to be rolled, what would be the probability? Well, the successful event of a 1 being rolled is on this branch. So that branch is 1 success out of 6. So for a 1 to be rolled, the chance is 1 out of 6. And what we'd write, and this is the proper format for writing the probability, we write P for probability, and then in the bracket here, we just write what is the successful event that we're looking for. So this would be read, the probability of rolling a 1 is 1 in 6. The probability of rolling a 5 would also be 1 in 6. In fact, the probability of rolling any side is 1 in 6. And 1 in 6 is 1 divided by 6, which is 0.167, which is 16.7, almost 17%. So there's almost a 17% chance of rolling any of the sides. So if you said, what's the chance of rolling a 2? It is about 17%, 1 in 6. Now, these probability trees can be used for more and more complex scenarios. So for instance, what would be the probability of rolling 2 6s in a row on one die? Now, one thing to try to understand is rolling 2 6s in a row on one die would actually be the exact same probability of rolling 2 6s on 2 dice at the same time. Okay? So you can use this exact tree for scenarios where you're rolling either multiple dice or one die. For example, the experiment I had you try to do yesterday was rolling 3 dice. We could use the idea of rolling one die 3 times, but you're about to see how complicated the tree can get for something like that, so we'll look at this example first. So here's what the tree looks like. Okay, and I know that's quite intimidating. It wasn't fun to draw for me either, but if you can start to visualize these in your head, it can start to make a little bit, what am I trying to say here? It can start to become more easy to, or easier, I should say, to do this kind of thinking in your head once you've seen one or two. And sometimes you don't have a choice. Sometimes you have to draw it out. There is a table that you can use to organize things too. But this really does help see, in my opinion, how this works. So our first roll is the exact same setup as the previous example. 1, 2, 3, 4, 5, 6 are the 6 possibilities when you roll one die, or one die once. But we're rolling it twice, or think of it as you could have, it says first roll and second roll here. This could be first die and second die, okay? So either one of those scenarios works. So the second roll, each one of the original branches has also 6 more possibilities. So if I roll a 1 on my first roll, I could roll any of the 6 sides of the die on the second roll. If I rolled a 2 on the first roll, same thing. I could roll any one of the 6 sides of the die on the second roll. So each one of these original branches has 6 more possibilities. And if you think mathematically, that means 6 times 6, right? So there are 36 branches down here. We were looking for 2 6s rolled in a row, okay? So what is the only full branch that has 2 6s in a row? Well, that only would happen over here because we'd have to roll 1 6, and then from these, figure out where we rolled the other 6. So this is the only branch, and this is all like one connection, okay? This is considered one success. So there's one success out of the total of 36. And that means the probability of rolling 2 6s is 1 out of 36. And 1 divided by 36 is approximately 0.027, which is 2.7%. So if you remember the percentage from the previous slide, to roll any of the 1 sides is 17% chance, but to roll 2 of the same sides one after the other is a 2.7% chance, which is much smaller. And each one of these branches actually has that same possibility. So if you wanted to know what is the chances of rolling a 1 and a 6 on 2 dice, or on one die, one after the other, you would find the 1 and the 6, which is a 1 out of 36 chance. And there are some gambling games, like if you think of the game of craps, if you've ever seen any kind of gambling on television or movies, there's a bunch of different specific rolls, but oftentimes they're trying to roll a 7 on 2 dice. So what are the chances of rolling a 7? Well, there are multiple chances of rolling a 7 by adding the 2 dice. So 2 and 5 right here is 1, 3 and 4, 4 and 3, 5 and 2, 6 and 1, 1 and 6. So there's a lot of different possibilities of rolling 7s. So we'll hopefully talk about that a little later. So like I said, there is a way to organize this kind of a tree in a table instead of the tree. And the way the tables work, and it is still pretty long to do, It's not that much shorter, but it might make sense to some of you to do it this way, and we might have to do it this way for some of our examples that are coming up. So what you do is you write down in a chart here, like all of your dice. So die roll 1, die roll 2, or you can think of this as 2 dice in a row. Either way works, okay? And then you list down all of the possibilities of what happens if you roll 1 first. So if I go back to the tree for a second, that would be this branch here. So starting with a 1, what are all of the possibilities after that? So starting with a 1, here are all the possibilities. Starting with a 2, what are all the possibilities? And then we'd have to do this for dice 1 equals 3. So all 3's here, every possibility. All 4's here, every possibility, until we get up to 6, which is the last possibility. So you'd have 6 different tables. You could have one long table, but that can be a bit of a difficult thing to do on a piece of paper. Okay, so I think if you just list the tables one next to the other, it's a little bit easier. And this has to be done for these kinds of questions. You can imagine with 3 dice, we would have every possibility with 3 dice. That means it would get a little bit more complicated, but we can do it, and we probably will do it in a little bit. And then you'd find the successes, which would be die 1 is equal to 6, die 2 is equal to 6, which again, looking at the tree above, would be this branch right here, and you'd get the exact same scenario. Okay? So you can use a table to organize these things too. Let's look at another example. This one might be actually a little bit easier. What about coin tosses? So what would be the probability of getting 2 heads in a row when flipping a coin? Well, the way we would write that, this is one way. You could write 2 heads in a row here, but probability of heads, right? That should make sense. And what would the tree look like? So giving you a chance to just think about it, what are the possibilities when you flip a coin? You can either get heads or you can get tails. So here's my coin, and here's my first branch. Okay, so you can get either heads or tails. In the second flip, and this also could be flipping 2 different coins. Okay, first flip, second flip, it could be 1 coin, second coin, or it can be 1 coin twice. The same probability either way. So in the second flip for heads, we've got heads or tails. And the second flip for tails, we have heads or tails. Those are the only 2 possibilities. We were looking for the probability of rolling heads twice. Well, here is my probability of rolling heads twice. And that means we have 1 success out of a total of how many outcomes. There are 4 possible outcomes here, which I want you to see is again 2 times 2, right? So there's a multiplication pattern that happens when you have a certain number of choices for the first time and a certain number of choices for the second time. It seems to be you just multiply the 2 numbers together, which is a power, right? An exponent, 2 squared. Just keep that in mind. And that means our probability of rolling 2 heads is 1 out of 4, which is 25% of the time. I believe that's the last. Oh yes, I just have one summary here that I'd kind of like to go over with you. So I just want you to remember one thing about the difference between theoretical probability and experimental probability. Okay, they are different. Theoretical probability means what should happen, and experimental probability means what does happen during an experiment. Everybody should have the same theoretical probability, but not everybody will have the same experimental probability unless the experiment was done a billion times. Okay, they say an infinite amount of times, and then the experimental probability starts to match exactly the theoretical probability. In practice, you would usually start to see this pattern after like a few thousand times. It would get, but it doesn't have to be. It doesn't have to get to theoretical probability until you've done it an infinite amount of times. So we have to try to keep those 2 things separate. Okay. So there will be a handout that follows this lesson, There's a few questions on that handout that I'd like you to try to figure out, and I will probably be correcting that in a video on Monday to show you what the correct answers are. But I would like you to try to do that handout today or over the weekend. That's it for today's lesson. The handout will be on the Google Classroom, so please take a look at that. Have a good day.